Welcome back. We are finishing up Unit 1 talking about infinite limits today. Two kinds of infinite limits. First, when the graph goes to infinity, or we could think about that as y values. And the second type is when the x values goes to infinity, and that we're talking about end behavior. Remember vertical asymptotes? Those are vertical lines that happen at some x value that makes the denominator of a rational function 0. So for both of these functions here, what makes the bottom 0? Well, at x equals 1, we would get a 0 denominator. But they're different graphs, so let's see what's going on. In this first one, if you look at the graph from the left, the graph is going up to infinity. If you look from the right, the graph is going up to infinity. So the limit, as x approaches 1, of the function is infinity. This one's a little bit different, isn't it? If you approach from the left, well, the graph's going up to infinity. But as you approach from the right, well, it's going to negative infinity. So those are going to different places. Both graphs come very, very close to the line x equals 1. Both functions have a vertical asymptote of x equals 1. But in calculus, we don't care only about the vertical asymptote. We actually are concerned about the behavior of the graph itself. So vertical asymptotes, they occur where a function approaches a positive or negative infinity as x approaches some number either from the left or from the right. Then the line x equals c is a vertical asymptote. So we'd say the limit as x approaches c from the left or from the right of the function is positive or negative infinity. A vertical asymptote occurs at a number at which the denominator is 0. However, a word of caution, we need to be sure to check for removable discontinuities, and I'll show you what that looks like. If we have this function, negative x over x plus 5, what would be the vertical asymptote? The denominator of the function is 0 at x equals negative 5, so there we have our vertical asymptote. How about this one? X squared plus 1 over x squared minus 4. Well, we could factor that, right, into x minus 2, x plus 2. So the denominator of the function is 0 at x equals plus or minus 2. And there we go. Oh, cotangent of x. Do you know the vertical asymptote of that off the top of your head? Let's rewrite it as cosine x over sine x. And if we have our unit circle here, sine of x is 0 anytime it's at the x-axis. So that's any multiple of pi, basically. All right, next one. X plus 3 over x squared minus 9. Okay, so the denominator of this function is 0 at x equals plus or minus 3. But wait a second, that's two numbers. And if you graph it, you only get one asymptote. So why is there only one asymptote at x equals 3? Because if you factor x squared minus 9, that's a difference of squares, you can cancel out the x plus 3 on the top and on the bottom. So what we're really graphing is 1 over x minus 3 with a whole at x equals negative 3. We'd call x equals negative 3 a removable discontinuity. So therefore, the vertical asymptote is only at x equals 3. Helpful limit properties. Let C and L be real numbers and F be functions such that. Okay, so F and G are both headed towards some x value of C. However, the graph of f of x as it approaches C goes to positive infinity, and the graph of g of x as it approaches C goes to L. Then the following properties apply. Remember, when we learned about limits, we learned that we can sort of distribute this limit through, okay? And so the limit as x approaches C of f of x is infinity, And as it approaches g of x, it's L. So what we really have here is infinity plus L, which is infinity. Here we would have infinity times L, which is infinity. But if L is negative, then we have infinity times a negative L, which is a positive times a negative, going to negative infinity. And then if we have L over infinity, anytime the bottom is growing really big, this whole fraction is getting closer and closer to 0. We've got the limit as x approaches 1 from the left of each of these functions. X squared plus 1 goes to 2, cotangent pi x goes to infinity. So what happens if you take the limit of x squared plus 1 over cotangent of pi x? That's 2 over infinity. The bottom's growing really big, so that's going to 0. Now we'll talk about horizontal asymptotes. So instead of y going off into infinity, what happens if x goes off into infinity? It should be an if. Typo, sorry. The line y equals L is a horizontal asymptote of the graph of f of x if the limit as x approaches negative infinity of f of x is going towards some number, or as x approaches positive infinity, the graph is going towards some number. This is referring to the end behavior of the function. So finding horizontal asymptotes of rational functions, that's when you have a polynomial in the numerator and the denominator. And what we're going to focus on are the leading terms of the top and the leading terms of the bottom. So if m is less than n, so we're looking at the exponents of each. If m is less than n, so if the bottom wins, the bottom is bigger, then the horizontal asymptote is at y equals 0. If the top wins, if the top is bigger, there is no horizontal asymptote. The graph is just going off into infinity. However, if m is just 1 more than n, then you get some slant asymptote. And then if it's a tie, this is really cool. If it's a tie, you're just looking at the coefficients of the leading terms, and that's your horizontal asymptote. So if we practice these, we've got a rational function. The end behavior of this, as x is going to infinity, what's happening to the graph? Well, in this case, 3 is bigger than 2. The bottom is bigger, so this graph is going to go to 0. There it goes. There's our horizontal asymptote at 0. And again, we're looking at that end behavior. This one, we've got 4 is bigger than 2, so the top wins. Therefore, this one is sort of infinity over 0. No limit exists on this one. It's just whoop, off it goes. To infinity, to infinity. This time, the top is just 1 bigger than the bottom. So you're going to have some sort of a slant asymptote. It still is going like off to infinity, positive infinity here and negative infinity here, but it's with a slant asymptote. And then finally, look at these 3's. That's the same number. So if it's a tie, then the asymptote is hanging out right there at the coefficients. So the asymptote is this line, y equals 9/4. I like those. What about non-rational functions? Those are a bit trickier. So you can approach different horizontal asymptotes from the left and from the right. You could graph it. You could chart it. If possible, you could solve analytically. So let's see a couple of those. Okay. See, it gets tricky with this, with that radical there. Here's the graph of the function. So you can see just from the graph, there's the end behavior to the right and to the left. Where is it actually going, though? It's hard to tell, but you can make yourself a table. So in the middle of the table, you're starting with some numbers close to 0. And then to the left, you get really negative really fast. And to the right, you get really positive really fast. And then you can look at the y values. What's happening to those y values? As we go to the left, as we go more and more and more negative, we're approaching -4. As we go to the right and get more and more positive, we're approaching +4. All right, limits with trig functions. I love trig functions. The limit as x approaches infinity of sine of x. Well, let's show us going up and down and up and down and up and down, right? So this is oscillating between not 0 and 1, but -1, sorry about that, and 1. So no limit exists. What about the sine of x over x? Let me fix this again. Here's the graph of that one, and it's still oscillating, isn't it? But it's getting closer and closer to a value. What value is it getting closer and closer to? And how do we prove that? Well, happily, we have the squeeze theorem we can use. So let me show you how this works. So sine is oscillating, like we said, between -1 and 1. But I want to know about sine of x over x. So I can just take all of these terms in this one and divide them all by x. Now if I graph -1 over x and +1 over x, ooh, look at, I can kind of see what's going on here. The orange graph, sine of x over x, is being squeezed by positive and -1 over x. So I can take the limit of each of those functions and see where they go. So the limit as x approaches infinity of -1 over x equals 0, and the limit as x approaches infinity +1 over x also equals 0. Therefore, sine of x over x is also squeezed into heading towards 0 as well. So now I'm just going to throw a bunch of stuff at you. Let's see what happens. The limit as x approaches 4 from the left of this rational function. Now, if you're looking at x approaches some number, not positive or negative infinity, probably looking for a vertical asymptote. It's hard to just see what makes the denominator 0. And anyway, we need to check for removable discontinuities. So we need to factor the top and factor the bottom. And see, we have this x minus 2 that we can cancel out. But here's a problem. We still have a 4 that if we plug in, we get a 0 on the bottom. That's not helpful. Because we're looking at what happens as x approaches 4 from the left, well, let's just plug in a number just to the left of 4, like 3.99. We can see what happens with that. On the top, we have some negative number. And on the bottom, this is also a negative number, but it's getting really, really, really small. And if something is really, really small on the bottom, that means this is going to infinity. So we have a negative number divided by a negative, really, really small number. So that's going to a positive infinity. So here we go. Whoop, there we go. Horizontal asymptote at x equals 4. But what about looking at as x approaches 4 from the right? Okay, same factoring on the top and the bottom, but we're looking at x approaches 4 from the right, so we'll plug in something just to the right of 4, 4.01. So we don't really care what this number is on top here, but we do care that it's negative. And on the bottom, we have a positive, really, really, really small number. So if you have a negative divided by a positive, really, really small number, that is going to negative infinity. This last problem that we're working on says use the function to find any vertical asymptotes that exist and then justify your answer using limits. So to find the vertical asymptotes, again, we're going to factor, cross out what we can. So At x equals -5, there's a hole. And then at x equals 2, we have a vertical asymptote. That's lovely. But you can't just say that. You have to justify your answer using limits. What does that look like? Okay, so we're going to approach our vertical asymptote from the left. So you plug in something just to the left of 2. And from the right, plug in something just to the right of 2. And you can kind of shortcut this because what you care about is, you know there's a vertical asymptote, but is the graph going to positive or negative infinity? So at 1.9, if you plug in 1.9, you get a positive over a negative number. If you plug in 2.1, you get a positive over a positive number. So at 2, there is indeed a vertical asymptote because the limit as x approaches 2 from the left, that's when we plugged in 1.9, that went to negative infinity, and 2 from the right went to positive infinity. There was a lot to learn in that one, but thank you for hanging in there with me. I'll see you in Unit 2.